Hello everyone and welcome back to the good stuff we have been doing. So today in this video we are going to try to evaluate this beautiful classic definite integral, which is the integral from 0 to infinity of cosine of ax divided by s squared plus b squared dx. Now we have already done this integral via two different methods so far. First one we use the fact that the Taylor series of cosine of ax is equals to the sum as n runs from 0 to infinity of negative 1 to the n x to the 2n divided by 2n factorial. And then we plugged it in and used the Cauchy-Shlomis transformation. So that it will be in the description below, the first solution. The second solution features the Laplace transform. So we recognize the fact that the inverse Laplace transform of the Laplace transform of f of x actually is equals to just f of x. So in that was the second solution. It's quite fast. I think it was about 9 minutes long. For this third solution here, we're going to use the fact that the inverse Merlin transform of the Merlin transform of what f of x is same thing as f of x as well. Now, this Merlin transform, unlike the Laplace transform, would be very long because we are going to make use of the Ramanujan Master Theorem. So we're going to make use of the Ramanujan Master Theorem. So, and also it requires a lot of series and substitution. But the reason I'm showing it is because it's a very beautiful solution, and it's not about being short or long. It's about the beauty, the aesthetic of the solution. That is the reason I'm going to show it, because it's too important for me not to show. Okay, so first of all, we are going to recognize the Ramanujan Master Theorem because it revolves around the Merlin transform. We know what the Merlin transform is. We know the Merlin transform of f of x. The Merlin transform of f of x is the same thing as integral from 0 to infinity of what t to the s minus 1 times f of t, or let's say x to the s minus 1 times f of x dx. So that is Merlin transform of f of x. So Ramanujan Master Theorem says that if the Merlin transform of f of x, so the Merlin transform of f of x, which we define to be the integral from 0 to infinity of x to the s minus 1 f of x dx. So this is equals to gamma of s times phi of negative s if it is possible that f of x be expressed as a series in such that f of x is equals to the sum as n runs from 0 to infinity of negative 1 to the n phi of n divided by n factorial x to the n. So if we can express f of x as a series in this form, then the Merlin transform of f of x is equals to gamma of s phi of negative s. And this is the Ramanujan Master Theorem. I made two videos discussing Ramanujan Master Theorem as well as examples of it. But now we're going to use the Merlin transform and this Ramanujan Master Theorem to actually solve this integral. So please sit back and do enjoy your time. So first of all, let's begin with the problem statement. We need to find the integral from 0 to infinity of cosine of ax all divided by x squared plus b squared dx. So we recognize this as f of a, and we know that the inverse Merlin transform of the Merlin transform of f of a is going to equal f of a. So basically this f of a, we could write it as the inverse Merlin transform of what? The Merlin transform of what? The integral from 0 to infinity of cosine of ax all divided by x squared plus b squared dx. Now the question now we ask ourselves is, what is the Merlin transform? Well, the Merlin transform in this case, this will be the inverse Merlin transform of what? Of the integral from 0 to infinity of, since it's an f in terms of a, it will be a to the s minus 1 times what? Times the integral from 0 to infinity of what? Cosine of ax times what? X squared divided by x squared plus b squared dx. Then you would then have the a. So this is now let's drop this inverse Merlin transform. First of all, we need to compute this double integral. So if we compute this double integral, whatever we get, we just find the Merlin transform. So because this double integral is in terms of dx and dA, so s is a constant. So whatever we get, we find the inverse Merlin transform of that. So we have the double integral from 0 to infinity. So let's just say, let's start on a fresh new page and let's change color. So we'll say that let us compute. So let us compute this double integral, which is the integral from 0 to infinity times the integral from 0 to infinity of what? You have a to the s minus 1 cosine of ax divided by x squared plus b squared dx and then dA. So first of all, we're going to do with respect to a first of all. So we have the integral from 0 to infinity of 1 over x squared plus b squared. Then you have to deal with the integral from 0 to infinity of a to the s minus 1 cosine of ax dx. dA then dx. Now this is, we are looking for the Merlin transform of cosine of ax. So this will be in terms of x, but this is a standard result, but we are going to try to prove it because we know that cosine of ax actually is equal to the real part of e to the negative ax, e to the negative iax. So we're going to use that fact and write the integral from 0 to infinity of 1 over x squared plus b squared times the integral from 0 to infinity. So we have a to the s minus 1 times the real part of what? E to the negative iax. Then you have the a, and then also you have the x. So if you continue from here, you could write this as the integral from 0 to infinity of 1 over x squared plus b squared. So let me shrink this out a bit so the solvings can fill up the page a bit. Yeah. So you would have the integral from 0 to infinity. I want to demarcate it so I don't burn too much pages here. So you have the integral from 0 to infinity of this. Then so you have the real part of what? So you have the integral from 0 to infinity of a to the s minus 1 e to the negative iax dA and then dx. What we'll do here is that we're going to take u, make a substitution that we're going to take u to just equal iax. Okay, then that means that leaves us that a itself, a would be u divided by ix, and basically dA would be du divided by ix. So so in this case you end up with the integral from 0 to infinity of what? You have a 1 over x squared plus b squared times the real part of, on this case of course the limit of integration will still be from 0 to infinity. So you have the integral from 0 to infinity of this a becomes, you have u over ix to the power of s minus 1. This one here you have e to the negative u, then you have du divided by ix, then you have dx. So on the flip side you still end up with this. So you have integral from 0 to infinity of 1 over x squared plus b squared. Then you still have to do the real part of, you factor out something here. So notice that ix is at the bottom. So you have a 1 over I to the s and then x to the x times the integral from 0 to infinity. The reason why we put that an x is because this only concerns a du. So you have u to the s minus 1 e to the negative u du and then dx. So now this is precisely going to be gamma of s. Obviously it's going to be gamma of s by definition of the gamma function. So this right here would equal the integral from 0 to infinity of what? 1 over x squared plus b squared times the real part of, now you have 1 over I to the s power x to the s power times what? Gamma of s. Then you have the x. So we can pull out gamma of s. So you have gamma of s and you have the integral from 0 to infinity. So you have x to the negative x divided by x squared plus b squared. You have to find the real part of 1 over I to the s power. So 1 over I to the s power is basically I to the negative s, and I itself is, we could define I, let me see, we could define I to be cosine of pi over 2 plus I sine of pi over 2. Point being that cosine of pi over 2 is 0, sine pi over 2 is 1. So this is e to the I pi over 2. So I to the negative s will be e to the negative I pi over 2 times s. So we could write this, we are looking for the real part of e to the negative I pi over 2s, and so we have dx. Notice though that the real part of this is basically cosine of pi over 2s, because cosine of negative x is still cosine of x. So you have, this is gamma of s, so you can factor out times cosine of pi over 2s times the integral from 0 to infinity of x to the negative s divided by x squared plus b squared dx. So let's zoom everything a bit now. So you see that our job is almost half, our job is basically half done. All we need now is to basically find this integral. We're going to compute this definite integral. It will be in terms of x, so whatever we get, say it will be f of s. Then we'll just find the inverse Merlin transform of all of it. Then we are able to have our definite integral done and dusted. Now you may ask, why do we use complex substitution here to do this? Well, this is because this is like the easiest method of approach. There are other ways to find this Merlin transform. One way is to use Ramanujan Master Theorem as well. Maybe I'll probably make a video of it using Ramanujan Master Theorem, because in this case you would involve to write this as a series, and then you will use the Ramanujan Master Theorem to compute it. So that one is not too long though, but this one is simpler for us here. So let's proceed. Now we need to evaluate these definite integrals. We need to evaluate, so we need to compute. So that is the integral from 0 to infinity of x to the negative s divided by x squared plus b squared dx. So how do we do that? Well, it's not too hard to do. We just need to be careful here. We will divide both sides by b squared. So this is going to be 1 over b squared times the integral from 0 to infinity of x to the negative s, all divided by 1 plus x squared divided by b squared. Then you have the x. So next up, what we need to do here is to make a substitution. We're going to boldly take t to be x squared divided by b squared, and point being that we want to have a 1 over 1 plus t at the bottom, so we can use our so-called geometric series, which says that 1 over 1 plus t is the sum as n runs from 0 to infinity of negative 1 to the n, then t to the n power. So this would allow us to use the Ramanujan Master Theorem, of course. So if we do this, notice that x squared becomes tb squared, which means that x would be square root of tb, and dx, importantly, will be 1 over 2 square root of t b. Okay, sorry, I lost connection a bit there. So x here would be square root of t b, where this allows us to notice that dx would be 1 over 2 square root of t b dt. So we now have our dx here, and also x to the negative s would be t to the negative s divided by 2 b to the negative s, and with that in hand, we'll write this as 1 over b squared. So we'll shift over and write this as 1 over b squared times the integral from 0 to infinity of course the limit of integration is still from 0 to infinity. So we'll have an x to the negative s, which will be t to the negative s over 2 b to the negative s, and at the bottom part you will have a 1 plus t. Then our dx would be b dt, all divided by 2 square root of t. So the square root of t and this t to negative x over 2 and this b here would make this to become 1 over b times the 1 over 2b rather, times the integral from 0 to infinity. Now over here you have a t to the negative s over 2 minus 1 over 2, and then all divided by 1 plus t, and then you have the t. So now we already agreed that 1 over 1 plus t has a series expansion as n runs from 0 to infinity of negative 1 to the n t to the n. So we could write this as 1 over 2b times this integral from 0 to infinity of t to the negative s over 2 minus half times the sum as n runs from 0 to infinity of negative 1 to the n t to the n, then dt. Here we know that according to Ramanujan Master Theorem, it says that the integral from 0 to infinity of t to the s minus 1 f of t dt is equals to gamma of s phi of negative s, where phi of s is related to the series expansion of f of t. So we already done the series expansion here. All that remains now for us is to just write this as 1 over 2b. Now we want to have an s minus 1. So we write this, I think we have a 1 minus s over 2 minus 1 should be so we have this as integral from 0 to infinity of t to the 1 minus s divided by 2. Then you would have minus 1. Then you have the sum as n runs from 0 to infinity of negative 1 to the n. So you have a gamma of n plus 1, which will be our phi of n. Then you divide by n factorial, and then you have a t to the n dt. So when all is said and done, you have 1 over 2b times what? So you have a gamma of s. So you have a gamma of 1 minus, you have a gamma of s times phi of negative s, where in this case our s here is same thing as our 1 minus s over 2. And gamma and phi of n and phi of negative s would be gamma of 1 minus s. So you have a, let's use a black color. So you have a 1 over 2b, and then you have a gamma of 1 minus s over 2, 1 minus s divided by 2. Then you have a gamma of 1 minus s divided by 2. And then here, if you use the reflection formula, you have 1 over 2b times pi divided by sine of 1 minus s over 2 pi. Now, this bottom part, this is a sine of pi over 2 minus s over 2 pi. Yes, so this will be sine of pi over 2 times cosine of pi over 2s. And then minus cosine of pi over 2, and then you have sine of pi over 2s. So this is 0, so this will be 1 times this. So this is cosine of pi over 2. So you have pi over 2b times 1 over cosine of pi over 2s. So let's see if we can go back and recollect some things. Now, if you recall, we left things over to this point and say that all we needed was to compute this. So here we have already computed that. So let's continue from here. This is where we left off. So this would equal to gamma of s cosine of pi over 2s. Okay, at this part here you have pi divided by 2b times cosine of pi over 2s. That is what we got. If we go back to check, that is exactly what we got here. Now we can from here make some cancellations, because we already see that both of these guys cancel out. So you have a pi over 2b times what? Gamma of s. So I hope that is but wait, there should be a mistake here. Okay, there is a b to the negative s here at the bottom. Yeah, so there should be a b to the negative s here. So we should have a b to the negative s factor. So that means we should have a b to the negative s factor. So if we go back to our our task here, we are going to find the inverse Merlin transform of all of these. So which basically means that the next thing is to find the inverse Merlin transform of this whole is equals to gamma of s, because I told you that it's going to be in terms of s. So it's gamma of s. Then you have, let me be sure, pi over 2b. So you have pi over 2b times 1 over times b to the negative s. Yeah, so we can factor out everything not concerning s. So you have pi over 2b. So you have the inverse Merlin transform of gamma of s b to the negative s. Now, if you remember the Ramanujan Master Theorem, this is like, we said the integral from 0 to infinity of t to the s minus 1, and then you have f of x is going to be t to the f of t rather dt is going to equal gamma of s phi of negative s. So basically here you can assume that phi of n is basically going to be b to the n power. So this means that this whole f of t would have a series expansion as n goes from 0 to infinity of negative 1 to the n, involving b to the n, x to the n, all divided by n factorial, because if you use the Ramanujan Master Theorem, so which is going to be e to the negative bx. But yeah, let's use a for our, we can use a for our sake because we are dealing with a. So basically this is going to be pi over 2b times e to the negative ab if you compute the inverse Merlin transform. So, and that is precisely what we got for the previous solutions we have offered to this problem. So this is the third solution so far. The first using the Cauchy-Chomley transformation, and also I think, yeah, and Taylor series technique. The second one uses the Laplace transform. This third one now uses the Ramanujan Master Theorem. So thank you very much for staying with me along this journey. And if you have a third solution, okay, yes, you can do this with residue theory, but we're not going to try such things here. It's not that it's bad, but this is supposed to be a unique channel where we offer unique ways to solve problems. This is a well-known configuration of a residue theorem, so that's why we're not going to go through that part. So thank you very much for watching, and please do subscribe to the channel. Bye and enjoy your day.